Okay, so welcome back. This is part 2 of counting principles and permutations. The problem we got in front of us is how many different arrangements or anagrams can be made from the letters in the word letter. Okay, so why don't you go ahead and pause that and see what you think you want to do with it. Alright, so hopefully you did that, and what we've got is 2 E's and 2 T's. Hopefully you noticed that. So if you didn't get 6 factorial over 2 factorial times 2 factorial, go ahead and pause this and type that in your calculator and then see what you get. Start it back up again when you get an answer. Okay, so if you did that, did you get 720? Well, I hope not, because if you did it wrong. And it's a really common mistake, and here's what's happening. I want you to notice this. In your calculator, if you type it in just like this, it's going to do 6 factorial divided by 2 factorial. But it doesn't know that you want to divide by both these things. It's going to do this divided by this, and then it's going to multiply the answer times 2 factorial, which is like doubling it. All right? So what you've got to do to fix that, or to keep, not from happening, is whenever you're going to divide by more than one thing, make sure you put those 2 things in parentheses. So 6 factorial divided by 2 factorial times 2 factorial should actually be 180. So hopefully that's what you got. All right, let's take a look at the next one here. How many different arrangements can be made from the letters in the word rock? All right, so R-O-C-K. We've got 4 distinct objects, and we're going to arrange all of them. So 4 factorial equals 24. Let's take a look at how many different ways or anagrams can we make from the letters in the word Mississippi. Pause this and try it on your own. Start it back up when you're ready. Okay, so hopefully you did that, and hopefully what you decided was that there are 11 letters, so it's 11 factorial, and then hopefully you said there's some identical letters here, and you looked for them, and you said, well, I got 4 I's, and hopefully you said, wait a minute, I got 4 S's, and then I got 2 P's, and so it's going to be 11 factorial divided by 4 factorial times 3 factorial times 2 factorial. And hopefully if you put them in your calculator, you're going to put parentheses around them so it groups them all together before it does the division. And then when you get that together, you should get 34,650. Okay, 3 strangers enter a room where there is one row of 6 seats that are empty. How many different ways could they sit in that row? All right, so I got these 3 guys. And they're going to sit in the seats, and one can sit here, and one can sit here. You notice how they don't say anything about having to be together. So they could be anywhere in these seats, and they can all be rearranged, all right? They want to know how many different ways that could happen. Well, a good way, or a way that I try to do to look at this, is kind of think about this. Okay, so yeah, there are these people or whatever, but what if I thought of them as being A, B, and C, all right? That's person number 1, person number 2, and person number 3. They're not identical. They're unique. And so I'm just going to give them letters A, B, and C. Now, the other 3 seats, well, they're going to be E's for empty. All right? And again, I know that they could be arranged any different way. But right now, if they sat together here, and then I would have this. So imagine this. I've got A, B, and C. And then I'm going to arrange them with these 3 E's, or these empties. And so if I told you I got these 6 letters here, and I asked you how many different ways they could be arranged, well, how would you do it? Go ahead and pause it and try it on your own. Okay, so hopefully you did that, and if you did, hopefully you got 6 factorial because there's 6 things, and we divided by 3 factorial because the E's are identical, and we found out there's 120 ways that people could sit like this. All right, look at this. We got these cereal guys, right? What if our problem is, in this case, we want to know how many different ways the characters can stand in a line, but snap, crackle, and pop, they always got to stand together. That's the way they always are. They always got to be together. And all the rest of the guys getting moved around, okay? Now, how are we going to do this? Well, a good rule of thumb is, again, when you have a condition that you start with it, and we know that snap, crackle, and pop must always be together. So we got to be careful in situations like this that we only apply the condition exactly as it's stated. You'll notice that it doesn't say that they have to stand in the same order. They just have to be together. All right, so let's take a look at this. One way to go about this is to think of these guys as one thing. All right? I got snap, crackle, and pop, and no longer I'm thinking of them as three things. I'm thinking of them as just one thing. And the strategy then is to go ahead and find the number of ways the new number of things could be found. Okay, so you'll notice now I've got 1, 2, 3, 4, 5 things. So what I want to do is find the number of ways I can rearrange the 5 things. And in this case, are there any identical items? Well, no, none of these guys are identical. And so it would look like this, 5 factorial. All right? Now, here's the part that's a little bit tricky, and some people have trouble wrapping their head around. All right, think about these guys the way they're standing right now. If I were to take and move the snap, crackle, and pop around, well, for example, the way these guys are standing right now, well, the snap, crackle, and pop could stand this way, but they also could move and rearrange themselves. And how many different ways could they rearrange themselves? Well, there's 3 of them, and they're unique, so I could rearrange these guys in 3 factorial different ways. So let's think about this. Here we got, first we've got snap, crackle, and pop together. And what if now they rearrange and then they move? And then they move again. And they move again. And what happens is that you'll notice the other guys haven't moved. So for every one of these different ways these guys are arranged, every time there's a new situation, these guys can switch positions, and they can do it 3 times 2 times 1 times. 6 different ways 3 people can stand in a row. So what happens is that once I go through and figure this, is when you get a problem like this and things got to be together, think about the together things as being one thing, and then find out how many different ways they can be arranged. But then you got to multiply it times the number of ways the together things can be arranged. All right, so let's take a look at this. 3 friends enter a room. There is 1 row of 6 seats empty. How many different ways could they sit in the row if they must sit together? Okay, so now you'll notice I've got A, B, and C. Again, 3 friends, and they're not identical. And I still have my 3 empty seats. But the difference here is that I'm going to think of A, B, and C, my 3 friends, as being one thing. So the question is, I've got 1, 2, 3, 4 things now, if I do that. And I'm going to divide it by 3 factorial because the E's are still identical. And so I have to divide by that. And then what is going to happen is that I ask myself, okay, then how many ways can the 4 things be arranged? Well, it's going to be 4 factorial divided by 3 factorial. But then I've got to multiply that by the number of ways my 3 friends can be arranged, which would be 3 factorial. So at the end of the day, this is going to be 4 factorial, which is equal to 24. All right? So just to kind of make this a little bit more clear, let's look at just the letters. All right? Now, I want you to imagine this. I got A, B, C, and then E, 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 right? And what happens is that if I consider A, B, C just one thing, say C, all right? Now, I can go ahead and I can rearrange this 4 different ways, all right? Now, you'll notice that, again, it doesn't make a difference. The E's are identical. So really, these are the only 4 ways that this can happen, all right? Now, for this way, the C could be ABC, ACB. There's 6 different ways. I know it seems kind of weird that 3 things can be arranged in 6 different ways. But take a look at them. Here's how it could work. All right? And in this configuration, there would be 6 different ways this would happen. And then in this configuration, there would be 6 different ways for that to happen. And then from this configuration, there'll be 6 different ways for this to happen. And then 6 more ways for the last configuration. I hope this makes it a little more clear about why we have to multiply at the end times 3 factorial. So, let's try this. Sometimes problems are permutation questions, but they do not use the word arrange or permutation. And quite honestly, in lower level, when you first learn permutations, you see these problems a lot. For example, they'll say, how many ways can 8 runners finish first, second, and third in a race? Well, again, if I'm thinking about the counting principle, I could say, okay, well, how many different ways can I fill in first place? And that would be 8. And then how many ways can I fill in second place? That would be 7. And then that would be 6 for third place. And I would get 336. And again, if you want to think of it as permutations, well, I've got 8 runners, and I'm going to find arrangements, and I'm going to take them 3 at a time, and that would also be 336. All right, now people usually get that the fact this is a permutation because order matters, because they think of first, second, and third place as being an order. All right, and obviously, if you come in first, it's different than if you come in second, okay, or third. And so people usually get this kind of problem, and they say, "Oh, order matters. It must be a permutation." Another example would be, say, how many different ways can a club of 20 people elect a president, a vice president, and a treasurer if the positions can be held by any member in the club? Well, again, it works the same way. I got 20, 19, and 18 different ways that the 3 spots could be done. Or again, if I think about it as permutation, I got 20 objects, 20 people, and I'm going to arrange them 3 at a time. And that would end up being the same number, okay? And hopefully you can see this is essentially the same problem. President and vice president and treasurer aren't like an order, first place, second place, and third place. Well, being selected, if I get picked for president, well, it's different than being picked for vice president. And so even though it's not an order, like first place, second place, or third place, this is still a situation where the way that you are selected makes a difference in the fact of what's happened. So that's why this is also considered permutation. All right, so let's try to pull some of this together. We've got the counting principle and the permutations. First, counting principle. Don't underestimate the counting principle. There's a whole lot of problems that can be solved using the counting principle that can also be used with permutations. Another thing, number 2, when you're given a condition, make sure that you consider it first. And it may mean you're going to look at the last digit or the last thing, but whenever given a condition, always try to deal with it first. And then number 4, this is a really biggie. Whenever you're arranging a number of objects and you're arranging all of the objects, well, it's going to be that number factorial. I'm sorry, this is number 3. So if you're arranging 5 things and you're arranging all 5 of them and they're distinct, then it's going to be that number factorial. And number 4, if you have a number of things, but some of them are identical, well, then what you've got to do is, take the number of things and do factorial, but then divide by any identical items, the number of them. And remember the parentheses if there's more than one of them. And then the last thing I've got written down here is if you are finding the number of arrangements of n things, but some of them have to stay together, think of the things that have to be together as one thing and find out all those arrangements. And then once you have those arrangements, keep in mind that for every one of those arrangements, your things that are together, well, they also can rearrange themselves. And so you've got to multiply the number of arrangements by the number of ways that your alone things can be also arranged. Okay, I hope you found this information helpful, and good luck on the quiz. Feel free to email me if you've got any questions or you need help with this. All right, thanks for watching.